Geometry students, here we are in chapter 2, and we're looking at inductive reasoning and conjecture. So our vocabulary words today include inductive reasoning, conjecture, and counterexample. So let's start off with inductive reasoning. What this refers to is basically the idea of looking at an example and then creating a rule. So looking at several examples and then creating a rule. So the idea of inductive reasoning to me makes me think about the way we discover a lot of mathematics, right? So what we usually do is we look at patterns in numbers and then we take that information and we might say, oh, well, this is always the case. For instance, I might say, like, look at perfect squares. So sometimes I play with numbers. Not often, but sometimes I do. So if you look at perfect squares, like 1 times 1 is 1, and like 2 times 2 is 4, and 3 times 3 is 9, and let's do some more. 4 times 4 is 16, and 5 times 5 is 25. If you think about the numbers on either side of 1, like 0 times 2, you get 0. I know this seems ridiculous, but watch this. If you take the number 2, the two numbers on either side of 2 are 1 times 3, like 1 and 3. 1 times 3 is 3. Maybe you're seeing something, 1, 0, 4, 3. Check this one out. The numbers on either side of 3 would be 2 and 4. 2 times 4 is 8. Wait a minute. 4, the numbers on either side of 4 would be 3 and 5. 3 times 5 is 15. The numbers on either side of 5 would be 4 and 6, and therefore you get 24. So what I'm hoping you see is you hear my voice getting more excited, like, oh my goodness, is that you see that the relationship, I'm not actually highlighting anything, the relationship here between the perfect square and then the product of the numbers on either side of that perfect square is that the product is always one less. And so I now have this several examples, and from this example I can inductively reason that if you take, so here's my little inductive reasoning, I might inductively reason that this is always going to happen. Okay, so that's what inductive reasoning is. Say, oh, this is always going to happen. So if I took a number like 360 and squared it, I would expect that 360 times itself, right? I'm expecting that 360 squared is going to be some number, whatever that is, that if I take 359 and I multiply by 361, that this answer, whatever it is going to be one less than that, right? Given the situation. And so that's what inductive reasoning is. So you look at several examples and you say, oh, this is the law. Now your conjecture is actually the formulation of that law. So I could say something like, so given this little inductive reasoning, here's my conjecture. All right, so I'm saying, okay, if n squared is equal to some number x, so if I have like some number n times n and it's equal to x, then n plus 1, that's the number after n, and n minus 1, that's the number before n. The product of those two is going to give me 1 less than the product of n squared, or it's going to give me x minus 1. I know this got real mathy real quick. Pause it and think about what I'm saying. This is a conjecture. It's just, hey, I'm saying, hey, this is what I see. I'm going to give you an idea. So a conjecture is basically kind of like a theory. All right, from my example, I see this happen, therefore this is going to happen. Just your little theory based on what's going on in your mathematical example. And we usually get conjectures through inductive reasoning. And the final thing is a counterexample. So here, sorry about that, here I have an idea, and a counterexample is an example that proves, whoops, yeah, so a counterexample is an example that proves the conjecture false. All right, and we're going to have a couple of examples about that. So inductive reasoning is going from examples to law. Conjecture is the statement of the law that you've gathered together, and a counterexample would be an example that proves the conjecture false. The fact is, I think this conjecture is true, so I can't prove it false, but you'll see that we'll do that in another couple of minutes when we look at some examples. So here we are. We're going to start looking at patterns of things and talk about conjecture. So we're going to write a conjecture that describes the pattern in each sequence, then use your conjecture to find the next item in the sequence. So basically, we're going to kind of look at some items. In this case, we have different times: 8:30, 9:45, 11 o'clock, 12:15, happen to be like movie times. Can you see anything here that looks like a pattern? What would you think the pattern would be of the movie times at this particular theater? So let's see. We can tell that 8:30 to 9:45 looks like the time elapsed is 1 hour and 15 minutes. And then here from 9:45 to 11 o'clock, that looks like another hour and 15 minutes. And then here from 11 o'clock to 12 p.m., we have another hour and 15 minutes. And so the show times seem to be what? The show times seem to be an hour and 15 minutes apart. So the show times at this theater are 1 hour and 15 minutes apart. That's our conjecture. Now, it asks us to use the conjecture to find the next items in the sequence. Well, this is pretty easy. We're just going to add on an hour and 15 minutes to find, I don't know, how many do they want me to do? To find the next item. So not the next items, but the next item. So I suppose the next movie will start in an hour and 15 minutes, which would be at 1:30 p.m. Make sense? All right, let's try this next guy. Ooh, look at this. It looks like a game that you might play with matchsticks, right? So you put matchsticks here, and then you see 4, and then 10, and then 18, and 28, and 40. And so whenever I see a system of numbers or a sequence of numbers, I would definitely look to see if there's any consistency in movement. So 4 to 10 is 6, 10 to 18 is 8, 18 to 28 is 10, 28 to 48 is 38, 12. And so I'm looking at these numbers, 6, 8, 10, 12. I would think that the next one would be a jump of 14. I'm thinking 54. Now, quite honestly, I don't feel like drawing this thing again. So what am I going to do? I'm going to first write the conjecture. So my conjecture is that the I should have put figure here. The figure, no, I didn't need that. Sorry about that. The increase, my bad. The increase in size of each figure is by 2 more than the previous increase. I know that looks crazy and it doesn't seem super clear, but what I'm saying is that the increase that happened for 8 from 10 to 18 is 2 more than the increase from 4 to 10, and that continues to happen. So how do I prove to myself that this next value is 54? And so I draw a picture here to convince myself that the 54 is true. And it does work, though my picture's kind of garbagey. All right, let's take a look at some algebraic and geometric conjectures. So here, we're going to make a conjecture about each value or geometric relationship. List or draw some example that support your answer. The sum of 2 odd numbers. So what we're doing is we're thinking, okay, if I add 2 odd numbers, so I go around, I think 3 plus 7 and 5 plus 1 and 6. That's not odd. You laughed at me. Sorry about that. 9 plus, I don't know, 11. And when I add these numbers together, 10, 6, 9, and 11, 20, I notice that all of these answers are super cute. No, I mean, all of the answers are even. And so my conjecture might be, so the sum of 2 odd numbers is even. That would be my conjecture. And then we're supposed to list or draw some examples that support our conjecture. And I feel like I have some here. And I can continue on with 1 plus, I don't know, 19 and 17 plus 51, and showing that each of these will yield will yield a positive even number. 7 plus 1 is 8, 5 plus 1 is 6. So that's basically what we're doing. So let's look at this. Segments joining opposite vertices of a rectangle. So for this investigation, I'm going to need some rectangles, which I have here. And I'm looking at these segments joining the opposite vertices. And I don't know about you, it looks like they might bisect each other. They might cut each other in half. And so that will be my conjecture. The diagonals of a rectangle bisect one another. And after that, I might um, draw some more rectangles and demonstrate that they certainly look like they bisect one another. All right. With that in mind, let's take a look at this example. Here we have the owner of a hair salon collects data about how many people come to her salon. Friday through Saturday, she collects this data for 6 months. And she's doing this to figure out what the deal is in terms of if she should hire more people. Great. So we take out the chart, and then we are asked to make a statistical graph that best displays the data. And the next thing we're asked to do is make a conjecture based on the data and explain how this conjecture is supported by our graph. And so what our textbook is doing is giving us an opportunity to flex our statistics skills by actually graphing something, and then also show us how we can use those skills to facilitate the process of conjectures. And so I cheated, and I actually simply just copied this from the book, because to make this chart would have taken a longer time than I want to spend on a video. So here's the picture of what's going on, and here's the statistical model. And you know, when you can look at something like this and see what's going on, it does give you some really detailed information. When you look at it like this, you can see that the total number of customers has been increasing pretty consistently over those 6 months by looking at this trend here. Let's see if I can make my pen do what I want it to do by looking at this trend here. And so from there we could make a conjecture and say, all right, if her business continues, it should still increase, and therefore she would want to hire more people. Let's look at another example. Our final example is about counterexamples, which we talked about a little bit in the beginning of the video, where we discussed that counterexamples prove a conjecture to be false, and that's what we'll do here. So here, if n is a real number, then n squared has to be bigger than n. And on the surface, that seems right. N is a real number, n squared is bigger than n, so you might try numbers like 3, 4, 5, 7, 9, and they all would bear out this conjecture. But when we try a number like n equals 1, right, 1 squared is not greater than 1. In fact, 1 squared is equal to 1. So you can see that it fails. This is a decent counter example. You could have also used n is equal to 1/2, or even something cool like n is equal to, I don't know, some other small number, 1/3 or negative 1/3 or something like that. Anyway, hopefully that kind of makes sense. Actually, the negative would not work, because if I threw a negative in there and I squared it, this would automatically be positive. So little numbers is what you need, 1 and lower than that. If JK is equal to KL, we're looking at part B, then K is the midpoint of JL. So if you have two segments where JK and KL are equivalent, then K is the midpoint of this segment JL. And they did a really good example, so I'm just going to reveal it. No, this is a counterexample, and the counterexample is JK and KL. JKL may not be collinear, right? So if JK here is equal to KL, but notice that K is not the midpoint of JL. And so hopefully that made a little bit of sense. Please check in with me. Let me know if I can do a better job explaining, and I look forward to seeing you guys soon. Take care.